Okay, welcome. In this video, we will be talking about exponential functions, modeling with exponential functions, how they relate to nature. So we can model many processes in nature using exponential functions. For example, we can model population growth really naturally. We can model radioactive decay, heat diffusion, many other different sorts of things. So here's the idea. With exponential growth, suppose we're interested in the growth of bacteria. So a particular population of bacteria begins with a single cell at the 0th hour, right? So this is how we would begin. At hour 0, we have one cell. After an hour, the population, that particular cell of bacteria divides. After another hour, each of those bacteria divide, so we have 4 bacteria. After 3 hours, each of those will divide, so we'll have 8 bacteria, and so on and so forth. So this kind of follows something pretty nice that we've seen before. So what does this look like? Take a moment to think about what this particular situation can be modeled by, what mathematical function. So let's write it down. At hour 0, we have 1 bacteria. After 1 hour, we have 2. After 2 hours, we have 4. After 3 hours, we have 8. These look like powers of 2, don't they? So this is 2 to the 0, 2 to the 1, 2 squared, 2 cubed. So this is pretty nice. And in fact, this is a really natural way of modeling a lot of different kinds of population growth. So if we started with 10 bacteria, would the pattern change at all? And the answer is no, because if we had 10 bacteria after 1 hour, we'd have 20. After 2 hours, we'd have 40. After 3 hours, we'd have 80. And this is really nice, because this is just 10 times 2 to the 0, 10 times 2 to the first, 10 times 2 squared, and 10 times 2 cubed. So this is just with the population doubling every hour. What do you think it would change very much if we were to say it doubled every 3 hours? Well, I think it would be pretty similar. It's just in this case we would have, at hour 0, we would have let's stick with our population of 10. We'd have 10, and then after 3 hours, we'd have our population of 20. After 6 hours, we'd have our population of 40. After 9 hours, we'd have our population of 80. So it still follows a similar kind of growth. This one we might write as, 10 times 2 to the 0 divided by 3. The idea here being that, do you know those flip clocks where after a full 60 seconds, a new panel with the next number flips down? That's kind of what's happening here, is after 3 hours, the next panel flips down and the population is doubled. So here would be 10 times 2 to the 3 divided by 3, 10 times 2 to the 6 divided by 3, and 10 times 2 to the 9 divided by 3. So we can write this pretty generally, and this is the idea here. If the initial size of population is n naught and the doubling time is a, then the size of the population at time t is represented by n of t equals n naught times 2 to the t divided by a. In this case, a and t are in the same unit. That should be somewhat intuitive, that whether that be minutes, hours, days, years, whatever, it doesn't matter. N naught is the initial population, could be 1, could be 2,876,000, and n of t is the population after some unit of time. So with this in mind, let's write quickly the equations from above. So in the case where we just had a single bacterium, go back to our green, we'll have n of t equals n, that should be equals 1 times 2 to the t. And this one was a simple case because we were just looking at population beginning with 1, doubles every hour. So you kind of think of this as being t divided by 1. The next one was n of t equals 10 times 2 to the t. So this one, the second one, we began with 10 bacteria, and we were still doubling every hour. And then the third one, I'll indicate what number these are, n sub 3 of t equals 10 times 2 to the t divided by 3. So now we're doubling every third hour, starting with a population of 10. We could write equations for different growth rates too. Like, we don't necessarily have to use 2. We could look at time to triple, and that might look like, so the time to triple, we would just use a base of 3 instead of 2, right? So that would be the same kind of idea as before. We would begin with some population n naught and triple every t over a units of time, or time to quadruple. We would write n of t equals n naught 4 to the t over a. So you kind of get the idea that we can really use any base that's intuitive for modeling a particular population or a particular situation. If we use the base e, this case, we don't really have a time to double. Instead, we use a relative growth rate that we call r. So in this case, we'll have this situation. A population that experiences exponential growth increases by the model n of t equals n naught e to the rt, where n of t is the population at time t, n naught is the initial population, r is the relative growth rate, and t is in time. So this should look pretty familiar to you. Maybe this looks a little bit like our friend PERT, right? This is compounding interest at some rate over some time. So, and just an example of this is if we stick with our bacteria example, we might have something like n of t equals, suppose we start with a population of 10,000 bacteria, and we grow at the relative growth rate of 1.4 times the population every hour. So t is in hours in this case, for t in hours. So this is what this would look like. In the next video, we'll work through some examples, talk through it, and look at converting between these two different models.